appearance. And the goal of the study I'm gonna present you today is to develop a new medicated wound dressing. So the context of this study for why we use wound dressing is to treat cutaneous chronic wounds. You may know that chronic wounds are diseases which are wounds which do not heal after 6 weeks. And among them, foot diabetic ulcers, venous leg ulcers, and pressure leg ulcers are the most common forms of chronic wounds. In Europe, 1.5 million people are affected by these diseases, and the worst consequence of these diseases are the leg amputation. That's why it's very important to treat them. And in France, for example, it costs 1 billion euros per year. The usual treatment is the wound debridement of the end, followed by a compression method with bandages. But sometimes it's not efficient to heal the wound, so a wound dressing application is required. A wound dressing can be made usually by biopolymer, alginate, if you know, but sometimes it's not efficient enough. So now the research orientates towards medicated wound dressing to accelerate the wound healing. Medicated wound dressing, it means in the wound dressing, you have a molecule which can promote wound healing. So in my lab, we have an expertise in dense collagen hydrogels. So a couple of years ago, we decided to evaluate collagen hydrogels as a novel wound dressing. Why? Because collagen is a protein, the most important protein in the world, in the body, sorry. And this collagen is biocompatible and biodegradable in the support of cell in the body. Hydrogels are highly hydrating, and the concentrated hydrogel have good mechanical and physical properties. So we thought it could be a promising materials to treat cutaneous chronic wounds. So what we decided to do is to encapsulate, of course, a drug. We encapsulate dexamethasone. It's an anti-inflammatory drug, and we studied the drug release from these collagen hydrogels. And as you can see on the screen here, unfortunately, the entire dose of dexamethasone was gone after a couple of hours. So we can say collagen hydrogels are bad drug delivery system. In the literature, you can find some drug delivery system added to collagen hydrogels, but unfortunately, as they are based on the formation of micro or nanoparticles, it's very difficult to encapsulate a high quantity of drugs. In addition, the hydrogels synthesized by other groups, they have bad physical property because they are synthesized from low concentrated collagen hydrogel. So the objective of this work was to develop a composite hydrogel associated dense collagen with a drug delivery system. In addition, we wanted to decide the composite to allow a high drug loading and a controlled release over 3 weeks because it's, you know, the kinetic required to treat chronic wounds. Oops, sorry. So we used a drug model, spironolactone. It's a hydrophobic drug which favors wound healing because our colleague treated daily some mice with spironolactone. They first performed a full thickness wound and they treated this wound with spironolactone, and what they observed, it was an acceleration in the wound healing after 5 days. Regarding the drug delivery system, we use polymer, we use polyesters, FDA approved because they are biodegradable. We used three kinds of polymers with different degrees of hydrophobicity. PLGA is the most hydrophilic, and PCl, polycaprolactone, the most hydrophobic. And PLGA, it's in terms of kinetic, has the faster degradation rate, and PCl the slowest. We use different chain lengths for each polymer. So we modulate the chain length and hydrophobicity to encapsulate spironolactone. Now let's take a look at the process of fabrication. So first, we used a concentrated collagen solution, and by raising the pH using ammonia, we form a dense collagen gel, and then we dehydrated them by tetrahydrofuran and incubated the hydrogel, the dehydrated hydrogel with polyester, PLGA, PLA, or PCl, and spironolactone dissolved in THF. Sorry. By incubating the mixture in the PBS, it's a phosphate buffer, it's a non-solvent, we trigger the in-gel nano-precipitation, and we form a hydrogel with some polyesters and drug encapsulated in this hydrogel. You can understand that the utilization of the polyester is to improve the drug encapsulation in the hydrogel. So now let's take a look at the structure of these hydrogels. Here on the panel B, you can see the fibrils, the collagen fibrils, characteristic of a collagen hydrogel. And when we added the polymers, PLGA, PCl, or PLA, you can see some particles at the surface of fibrils, and it was polydispersed from the nano scale to the micro scale, but the average size of particles was bigger when the chain length increased. And if you compare PLGA1 and PCl, means a polymer with the same size but not the same degree of hydrophobicity, when the hydrophobicity was higher, the particles were bigger. Now we analyze the interaction between collagen and the polyester by Ftir, and if you take a look at the panel 1, for example, you have the spectrum of collagen and the spectrum of PLGA1, and the spectrum of the composite material was the merge of these two spectra, suggesting the absence of a strong interaction between the polymer and the polyester. And it was exactly the same, the same thing for the other polymers. So now let's take a look at the physical properties. We managed to immobilize a large quantity of polymer inside the collagen hydrogel because the fraction of polymers was from 30% to around 45%, but with the most hydrophilic polymer, the fraction was bigger compared to the polymers with a high degree of hydrophobicity. Then we measure the swelling ratio. Why we measure the swelling ratio? Because it's very important to calculate the degree of hydration. Here you have the pure collagen with a very high swelling ratio, but when you add a polymer, you decrease by 50% the swelling ratio, and this swelling ratio was lower with the PLGA, and this could suggest an interaction between PLGA and collagen. But what it's important to say, it is despite a lower degree of hydration compared to collagen, this degree of hydration was more than 90%, and it's very important to treat chronic wound. Then we measure the mechanical properties by rheology, and here you have the storage modulus of collagen, and on the right you have the composite made with PCL and PLA, and you can see we didn't see any difference in terms of mechanical properties. In contrast, when the PLGA was used, PLGA 1 and PLGA 2, we doubled the storage modulus of collagen hydrogel, and when we used PLGA 3, we tripled the storage modulus, suggesting one more time an interaction between collagen and PLGA. As we want to handle and to apply this wound dressing in the wound bed, we measure the deformability of the collagen-polyester composites. And here you have the collagen, and we decrease a little bit the deformability by the presence of the polymers, but it was acceptable around 40%, except for PLGA 3. So as the initial goal was to add a drug delivery system to collagen to speed up the wound healing, we measure the drug loading and the release kinetic. So here you have the collagen, and you imagine, and you can see, the presence of polymers had a positive effect in terms of drug loading, of course, because we use a hydrophobic drug and we use polyester, and these polyester are also hydrophobic. So we managed to encapsulate a large quantity of drug compared to collagen. What about the release kinetic? Here you have the collagen. Everything is gone in 2 days. And if you take a look at the pink and the green curves, you see a linear release over 21 days. And the pink is PLGA 1 and the green is PCL. And you can, for these polymers, you can get a sustained and controlled release over 21 days. So we modelize the release kinetic. And what we saw, we calculated the N value, and the N value represents, the mechanism of release. I mean, if the N value is around 0.5, it means the release is based on diffusion, and when it is 1, it's more erosion. And for PLGA 1, you can see here we are in between. So the diffusion, the release is based on diffusion plus erosion, but for the other polymers, we calculated a N value at 0.5. It means the release kinetic is based on diffusion, for example, for PCL. But when we analyze the degradation of our composite hydrogels, we saw, of course, an erosion for the PLG1, but surprisingly, we also saw a degradation for PLGA2, but according to the models, the release was about diffusion. So maybe we can say the erosion phenomenon is not important in this case. So we compare our system, I mean by nano precipitation, with hydrogels made with particles. And what you can see here, when you use nanoparticles and you encapsulate these nanoparticles loaded with spironolactone inside a collagen hydrogel, the release kinetic is very fast, with the same quantity of drug. Is very fast over, I would say, 10 days instead of 21 days, but you improve the mechanical properties. When we used microparticles, in this case, the release kinetic was sustained and controlled, but we didn't improve the mechanical properties. So with the procedure of in situ nanoprecipitation of polyesters, we can get a sustained and controlled release plus improved mechanical properties. So to finish off, we measure the cytotoxicity of these composite hydrogels on cells, dermal cells, and keratinocytes. And regardless of the polymer studied, we didn't see any cytotoxicity on dermal fibroblasts, because when the cells are colored in the in green, if they have some green fluorescence, it means they are alive. If they are red, they are dead. And we observe the same thing with keratinocytes. Most of the cells were green. And to finish off, we assess the effect of spironolactone released from collagen PLG1 because it is at the most promising material. So we perform a full thickness wound and we applied on the top hydrogels. And what we saw here, after 10 days, the wound was completely closed. Okay, so our composite hydrogels had an impact. So to conclude, we can say that collagen PLGA 1 means with the chain lengths from 7 to 17 kilodalton, composite hydrogels are promising wound dressing to treat cutaneous chronic wound because the nanoprecipitation leads to a high content of polymers and lipophilic drug using dense collagen hydrogels. The composite hydrogels are highly hydrated. They exhibited high mechanical properties and they are not toxic for cells. We can get some sustained and controlled release from spironolactone over 3 weeks. And in vivo, in the model of mouse, we can improve the wound closure of the skin. So thank you very much. And I would like to thank my collaborator in my lab at the LCMCP and my collaborator at the Hospital Saint-Antoine and the Centre de Recherche des Cordes. Thank you very much.
We have time for a question. If someone has a question.
Have you ever worked with bacteriocellulose?
Say it again. What?
Bacteriocellulose hydrogels. Have you ever worked?
Bacterial, yeah, but a long time ago. Yeah. It's very difficult because usually, usually they are not good for that. You know. Yeah. The films are better for that. Yeah.
Please.
Yeah.
Thank you very much for this presentation. How did you measure the mechanical properties?
So we did 2 things, maybe biorheology for the storage modulus. Yeah, well, sorry. Here and by traction for.
How did you measure the traction?
Until it's breaking. So you have the machine and you pull until it breaks.
Okay, it's in constant.
Sorry.
It's in constant state.
Yeah.
Okay, thank you very much. We follow that.